From the very beginning of Richard Feynman's life, curiosity was not something separate from who he was. It was the way he existed in the world. It was not a hobby, not a professional requirement, and not a personality trait he switched on only in the laboratory. Curiosity for Feynman was a constant inner motion, a refusal to accept the surface of things as sufficient. As a child growing up in New York, he was surrounded by ordinary objects, everyday events and simple experiences, yet none of them were ever ordinary to him. His father played a crucial role in shaping this mindset. Instead of naming things for the sake of memorization, he taught young Richard to ask what those things did, how they worked, and why nature behaved the way it did. When they walked together and saw a bird, his father did not say, "That is a sparrow," and stop there. He explained how the bird survived, how it searched for food, and how its behavior fit into the larger pattern of nature. The name was irrelevant, the understanding was everything. This early training planted a deep idea in Feynman's mind: knowing the label of something is not the same as knowing the thing itself. That distinction became one of the guiding principles of his entire intellectual life. He learned to distrust shallow explanations and empty authority. If someone claimed something was true, Feynman felt an almost physical need to understand the reason behind it. Curiosity, for him, was not satisfied by answers that relied on tradition, reputation, or consensus. He wanted to see the mechanism, the logic, the connection between cause and effect. This hunger for understanding followed him into school, where he quickly realized that many educational systems valued correct answers more than deep thinking. While other students focused on passing exams, Feynman focused on figuring things out for himself, even if it meant taking longer or going against the expected method. As he grew older and entered the world of advanced physics, curiosity became both his greatest strength and his defining signature. Quantum physics was a field full of strange rules, counterintuitive behavior, and mathematical formalism. Many accepted these rules as facts to be used rather than mysteries to be explored. Feynman could not do that. When he encountered an equation, he did not simply learn how to apply it. He wanted to know where it came from, what it meant physically, and how it connected to reality. If he could not form a mental picture, even an imperfect one, he felt dissatisfied. This attitude often led him to unconventional paths. While others followed established methods, Feynman asked whether there was a simpler, more intuitive way to arrive at the same result. Sometimes this curiosity led to mistakes, but he never feared being wrong. To him, being wrong was a natural step toward being right. Curiosity also shaped the way Feynman interacted with problems that seemed unsolvable. Instead of being intimidated, he felt energized. A difficult problem was an invitation, not a threat. He approached it playfully, trying different angles, questioning assumptions, and even breaking the problem down into absurdly simple parts just to see what would happen. This playful curiosity was not childish, it was disciplined and persistent. He could spend hours, days, or even years circling the same question, driven not by external pressure but by an internal desire to understand. This mindset was crucial in his work on quantum electrodynamics, where existing theories produced infinities that made no physical sense. Many physicists accepted these infinities as technical nuisances. Feynman could not. His curiosity demanded a deeper explanation, and that demand eventually led to new ways of thinking that transformed the field. What made Feynman's curiosity so powerful was that it was never limited to physics. He was curious about everything: biology, chemistry, art, music, language, psychology, and human behavior. He learned to play the bongo drums not to impress anyone, but because he wanted to know what it felt like to create rhythm. He studied drawing because he wanted to see the world more accurately, to understand how perception works. He learned foreign languages out of sheer interest in how different cultures expressed ideas. This broad curiosity enriched his scientific thinking. He saw connections where others saw boundaries. For Feynman, nature was not divided into separate subjects, it was a single, interconnected reality. and curiosity was the thread that allowed him to move freely within it. In teaching, this same curiosity became contagious. Feynman did not stand in front of students as a finished product delivering final truths. He stood there as a fellow explorer, inviting them to think along with him. He often reconstructed ideas from the ground up, asking the same questions a beginner might ask, even if the answers were already well known. This was not an act, it was genuine. He believed that every time an idea was explained, it should be rebuilt in the mind, not simply repeated. His curiosity about how students thought was as strong as his curiosity about physics itself. He paid close attention to where they became confused, where their intuition failed, and where standard explanations broke down. Those moments of confusion fascinated him, because they revealed gaps in understanding that needed to be addressed. Feynman's curiosity also made him resistant to intellectual arrogance. Despite his fame and recognition, he never believed that being an expert meant being finished learning. On the contrary, expertise, in his view, increased responsibility. The more one knew, the more one should question. He often criticized scientists who used complicated language to hide a lack of understanding. For Feynman, complexity without clarity was a warning sign. His curiosity pushed him to strip ideas down to their essentials, even if that process exposed uncertainty or ignorance. He was comfortable saying, "I don't know," because curiosity thrives on that admission. Not knowing was not an embarrassment, it was an opportunity. Another crucial aspect of Feynman's curiosity was his refusal to separate thinking from direct experience. He believed that curiosity should be grounded in observation and experiment. Abstract thinking was valuable, but only when it remained connected to reality. He loved simple experiments, even crude ones, because they revealed how nature actually behaved, not how people assumed it behaved. This attitude protected him from becoming lost in purely theoretical speculation. Curiosity, for him, was always aimed outward toward the world, not inward toward intellectual status or personal validation. Curiosity also shaped Feynman's ethical stance as a scientist. He believed that genuine curiosity required honesty. If one manipulated data, ignored inconvenient results, or pretended certainty where none existed, curiosity was being betrayed. His participation in the investigation of the Challenger disaster later in life demonstrated this principle vividly. While others relied on reports and formal procedures, Feynman asked simple, direct questions and performed straightforward demonstrations. His curiosity cut through bureaucracy and revealed the truth. This episode showed that curiosity is not only a tool for discovery, but also a safeguard against self-deception and institutional failure. As the years passed, Feynman became increasingly concerned that curiosity was being discouraged in education and society. He observed that many students were trained to pass tests rather than to think. He worried that science was becoming a collection of techniques rather than a living process of inquiry. Through his lectures, books, and public talks, he tried to reignite curiosity wherever he could. He reminded people that the pleasure of finding things out was one of the greatest joys available to the human mind. This pleasure, he argued, was universal. One did not need to be a genius to experience it, one only needed the courage to ask questions and the patience to pursue answers. In the end, curiosity defined Richard Feynman more deeply than any title or award. It shaped how he learned, how he taught, how he worked, and how he lived. It allowed him to make quantum physics accessible, not by simplifying it beyond recognition, but by approaching it with the same wonder and honesty that a curious child brings to the world. His life stands as a powerful reminder that curiosity is not something we grow out of when we become adults or experts. It is something we either protect and cultivate, or slowly allow to fade. Feynman chose to protect it fiercely, and through that choice, he transformed not only his own understanding, but the understanding of countless others who learned to see curiosity not as a weakness, but as the very foundation of true knowledge. Curiosity, for Richard Feynman, did not slow down or soften as he matured, it sharpened. As his career advanced and his reputation grew, curiosity became less about proving intelligence and more about protecting freedom of thought. He became increasingly aware that success itself could be dangerous. Recognition, awards, and authority often tempt people to stop asking questions, to defend their position instead of exploring new ideas. Feynman resisted this temptation with unusual determination. He deliberately avoided situations where he felt pressured to act like an unquestionable expert. He preferred environments where he could remain mentally playful, where he could experiment, fail, and rethink without fear of embarrassment. Curiosity, in his mind, required a certain humility, the willingness to admit that nature is always smarter than we are. This attitude influenced the way he approached collaboration with other scientists. Feynman did not engage in intellectual competition for prestige. He engaged in shared exploration. When discussing ideas, he listened closely, not to find flaws in others, but to discover angles he had not yet considered. At the same time, he never hesitated to challenge ideas that did not make sense to him, no matter how respected their source. His curiosity was loyal only to understanding, not to people or institutions. This made him both admired and, at times, unsettling to colleagues who were more comfortable within established hierarchies. Yet even those who disagreed with him recognized that his questions often revealed hidden assumptions everyone else had overlooked. Feynman's curiosity also expressed itself through his relationship with mathematics. While he was highly skilled mathematically, he did not worship equations for their own sake. To him, mathematics was a language nature used, not the essence of nature itself. If an equation worked but he did not understand what it was saying about reality, he felt uneasy. He often searched for alternative formulations that matched his intuition more closely. This desire led him to develop methods that were not only powerful, but also conceptually transparent. His curiosity pushed him to ask not just whether something worked, but why it worked in that particular way. This insistence on meaning over formalism helped bridge the gap between abstract theory and physical insight. Curiosity also shaped Feynman's resilience. Like all great thinkers, he encountered moments of deep frustration when progress seemed impossible. There were times when problems resisted every approach he tried. Instead of forcing solutions, he learned to step back and let curiosity guide him indirectly. He would work on unrelated problems, play music, or engage in other interests, trusting that his mind would continue exploring in the background. Often, insights arrived unexpectedly, not through intense effort but through relaxed attention. This taught him an important lesson: curiosity thrives when the mind is open, not strained. He understood that forcing understanding can sometimes block it, while genuine interest keeps the mind flexible and receptive. In his personal life, curiosity made Feynman unusually attentive to everyday experiences. He noticed patterns in conversations, behaviors, and social dynamics that others ignored. He was fascinated by how people thought, why they believed what they believed, and how easily they could deceive themselves. This curiosity sometimes made him skeptical of social conventions and cultural norms. He questioned rituals, traditions, and moral rules not out of disrespect, but out of a desire to understand their origins and consequences. This questioning occasionally brought criticism, but Feynman accepted that curiosity often comes with discomfort. He believed that comfort is rarely a reliable guide to truth. One of the most striking aspects of Feynman's curiosity was his refusal to romanticize science. While he found nature deeply beautiful, he did not turn science into a source of false certainty or emotional security. He accepted ambiguity as an essential part of reality. Quantum physics, after all, teaches that uncertainty is not a temporary limitation, but a fundamental feature of the universe. Instead of resisting this idea, Feynman embraced it. His curiosity allowed him to be comfortable living with unanswered questions. He famously argued that doubt and uncertainty are not threats to meaning, but sources of wonder. The fact that we do not fully understand the universe makes it more interesting, not less. This perspective deeply influenced his teaching philosophy. Feynman believed that education should not aim to eliminate confusion too quickly. Confusion, when handled honestly, is a sign that learning is happening. He often allowed students to sit with difficult ideas without immediately resolving them, encouraging them to explore different interpretations and test their intuition. This approach contrasted sharply with traditional teaching methods that prioritize clear, final answers. Feynman understood that real understanding develops gradually, through repeated questioning and refinement. Curiosity, therefore, needed time and patience. It could not be rushed. As his lectures became widely known, Feynman became increasingly aware of his responsibility as a communicator of science. He recognized that curiosity could be fragile, especially in beginners. A single humiliating experience, a dismissive response, or an overly complicated explanation could extinguish it. This awareness made him particularly careful when addressing fundamental questions. He never mocked simple inquiries. On the contrary, he valued them because they often pointed to deep conceptual issues that experts had learned to ignore. By treating curiosity with respect, he created an environment where students felt safe to think freely. Feynman also saw curiosity as a moral responsibility in a world shaped by science and technology. Scientific knowledge grants power, and power without curiosity can become dangerous. If people stop asking how things work and what consequences they have, they risk causing harm without understanding it. Feynman believed that curiosity keeps science aligned with human values by forcing continuous reflection. This belief was shaped by his experiences during World War II, when he worked on the Manhattan Project. While he contributed to the technical success of the project, he later reflected deeply on its ethical implications. Curiosity, for him, extended beyond technical achievement to include questioning the broader impact of scientific work. As he grew older, Feynman's curiosity did not diminish even as his health declined. He continued to ask questions, explore new ideas, and challenge assumptions. He remained fascinated by the unknown, accepting that his time was limited but his curiosity was not. This lifelong commitment to inquiry gave his life a sense of coherence and vitality. He did not see learning as preparation for life. Learning was life. Every day offered something to understand more deeply, something to question, something to appreciate. In the final analysis, curiosity as a way of life was the foundation upon which everything else in Richard Feynman's career was built. It enabled him to make quantum physics accessible not by reducing its depth, but by approaching it with openness, honesty, and joy. His curiosity dissolved barriers between expert and beginner, between complex theory and simple intuition, between science and everyday experience. It showed that understanding does not begin with intelligence or talent, but with the courage to ask questions and the persistence to follow them wherever they lead. Through this way of living, Feynman left behind more than scientific discoveries. He left behind a model of how a human mind can engage with the universe honestly, creatively, and without fear. One of the greatest challenges in quantum physics is that it describes a world that cannot be directly seen, touched, or experienced with human senses. Electrons, photons, probability waves, virtual particles, and quantum fields do not behave like everyday objects. They exist in a realm where intuition fails and common sense breaks down. Before Richard Feynman, much of this invisible world was locked behind layers of dense mathematics and abstract formalism. It was accurate, but it was distant. Many students and even physicists learned how to calculate results without ever feeling that they truly understood what was happening. Feynman sensed this gap immediately, and it bothered him deeply. For him, understanding was not complete until the invisible could be made mentally visible. Feynman believed that the human mind needs images, stories, and physical intuition to grasp reality, even when that reality is abstract. He did not claim that quantum phenomena could be visualized perfectly, but he believed strongly that partial, imperfect mental pictures were far better than none at all. Mathematics, in his view, was a powerful tool, but it was not understanding by itself. An equation could give the right answer while leaving the mind empty. Feynman wanted to fill that emptiness. He wanted students and scientists to feel that quantum physics, strange as it is, still described something real happening in the universe. This belief drove him to search relentlessly for ways to translate invisible processes into understandable forms. One of his most revolutionary contributions came from this desire, the development of what later became known as Feynman diagrams. At their core, these diagrams were not originally meant as mere calculation shortcuts. They were visual stories of particle interactions. Lines represented particles moving through space and time. Vertices showed interactions. Suddenly, processes that were previously buried inside complex integrals could be drawn on paper and followed step by step. Even though the diagrams were symbolic, they allowed physicists to see interactions unfolding. The invisible became traceable, almost tangible. What made this approach so powerful was its honesty. Feynman did not pretend that these diagrams were literal pictures of reality. He openly stated that they were tools for thinking, not photographs of nature. But that distinction was precisely what made them effective. By acknowledging their limitations, he freed people to use them creatively without mistaking them for absolute truth. This balance between imagination and rigor was central to how he made quantum physics understandable. He showed that you could respect the mystery of nature while still building intuitive bridges toward it. Feynman applied this same philosophy in his teaching. When he explained quantum mechanics, he did not start with axioms and postulates. He started with questions that mirrored the confusion of the listener. He openly admitted that quantum behavior does not match everyday experience, but instead of stopping there, he explored what that mismatch meant. He used analogies drawn from daily life, even when they were imperfect, because they gave the mind something to hold on to. He preferred a slightly flawed intuition over a perfectly memorized formula. To him, understanding grew from engagement, not from passive acceptance. A striking feature of Feynman's explanations was his ability to move between levels of description. He could talk about a physical process qualitatively, then shift into mathematics, then return to plain language without losing coherence. This movement helped listeners connect symbols to meaning. Many teachers either stayed entirely in mathematics or avoided it altogether. Feynman refused both extremes. He believed that accessibility did not mean avoiding difficulty, it meant guiding people through it step by step, showing how abstract symbols corresponded to real processes in nature. Another key aspect of making the invisible understandable was Feynman's emphasis on process rather than static facts. Quantum physics is not about objects sitting still, it is about interactions, changes, and probabilities evolving over time. Feynman focused on what things do, not just what they are. He described particles as events, interactions as conversations between fields, and forces as exchanges rather than mysterious influences at a distance. This dynamic perspective helped students move away from rigid classical images that no longer applied. The invisible world became active and alive, not frozen and incomprehensible. Feynman was also deeply aware of the danger of false clarity. He knew that some explanations sound simple but hide confusion underneath. He actively fought against explanations that relied on vague words without clear meaning. If a concept could not be expressed precisely, he questioned whether it was truly understood. At the same time, he resisted the opposite danger hiding behind complexity. When people used complicated language to explain quantum phenomena, Feynman often suspected that they were masking uncertainty. His goal was clarity without dishonesty. Making the invisible understandable required courage, because it meant exposing what was not yet fully known. In his lectures, Feynman often emphasized that quantum mechanics does not allow us to say what is happening in the classical sense, only what is likely to happen. Probability, for many learners, feels unsatisfying. It seems like ignorance rather than knowledge. Feynman reframed this idea. He explained that probability in quantum physics is not a temporary lack of information, it is a fundamental feature of reality. By explaining this clearly and repeatedly, he helped students accept a worldview that did not promise certainty. Understanding, in this context, did not mean replacing uncertainty with certainty, but replacing confusion with clear limits. Feynman's talent for making the invisible understandable was not limited to formal teaching environments. In conversations, interviews, and public talks, he used the same approach. He spoke to non-scientists with respect, never assuming that complexity was beyond them. He believed that anyone could grasp the core ideas of quantum physics if they were explained honestly. This belief was radical at a time when many scientists saw public understanding as either impossible or unnecessary. Feynman rejected intellectual elitism. He saw understanding as something to be shared, not guarded. One reason Feynman succeeded where others struggled was his deep empathy for the learner's perspective. He remembered what it felt like not to understand. He did not erase his own confusion once he had mastered a topic. He preserved it as a reference point. This allowed him to anticipate where explanations would fail. He paid attention to the exact moment when intuition broke down and focused his efforts there. Making the invisible understandable required not only brilliance, but patience and humility. Feynman had both. He also understood that understanding often comes in layers. A first explanation may only provide a rough picture. Deeper understanding requires revisiting the same idea from different angles over time. Feynman encouraged repetition without boredom by changing perspectives. He would explain the same concept using different analogies, different mathematical forms, and different physical interpretations. Each pass added depth. This approach respected the complexity of quantum physics while still keeping it accessible. Importantly, Feynman never promised complete understanding where none was possible. He openly stated that nobody truly understands quantum mechanics in an intuitive classical sense. But instead of presenting this as a failure, he presented it as a fact of nature. The goal, then, was not perfect intuition, but useful intuition. Understanding meant knowing what questions could be asked, what predictions could be made, and where intuition must stop. By defining understanding this way, Feynman made peace with the limits of human perception without surrendering to mysticism or despair. Feynman's approach transformed the emotional relationship people had with quantum physics. Fear and intimidation were replaced with curiosity and engagement. Students no longer felt excluded from the subject simply because it was strange. Strangeness became part of its appeal. The invisible world of quantum phenomena, once distant and abstract, began to feel like a natural extension of reality, governed by rules that could be explored, questioned, and partially understood. This ability to make the invisible understandable was not an accidental talent. It was the result of deliberate effort, guided by a deep respect for truth and for the human mind. Feynman believed that nature deserves to be understood as clearly as possible, and that people deserve explanations that do not insult their intelligence. By building bridges between mathematics and meaning, between abstraction and intuition, he changed not only how quantum physics was taught, but how it was experienced. Through his work, the invisible did not become simple, but it became approachable, and that shift opened the door for countless minds to enter a world they once believed was closed to them. Making the invisible understandable also required Richard Feynman to confront one of the deepest psychological barriers in learning quantum physics, the fear of contradiction. Classical physics trains the mind to expect consistency with everyday experience. Objects have positions, causes precede effects, and events unfold in predictable ways. Quantum physics violates these expectations repeatedly. Particles appear to interfere with themselves, outcomes depend on probabilities, and measurement seems to influence reality. Many learners respond to this by either rejecting quantum ideas outright or accepting them mechanically without true understanding. Feynman recognized this reaction and addressed it directly. He taught that the discomfort itself was meaningful. It signaled the boundary between classical intuition and quantum reality. Instead of trying to force quantum behavior into familiar categories, he encouraged learners to let new patterns form, even if they felt unstable at first. A central element of this process was Feynman's insistence on separating description from interpretation. He made it clear that quantum mechanics does not tell us what nature is. In a philosophical sense, it tells us what nature does in measurable ways. This distinction was liberating. It allowed students to focus on observable consequences rather than metaphysical speculation. By grounding understanding in experimental results, Feynman helped people navigate the invisible without becoming lost in abstract debates. The unseen world became something that could be explored methodically, not mystified or mythologized. Feynman was particularly skilled at explaining why classical intuition fails at small scales. He did not treat this failure as a flaw in human thinking, but as a natural consequence of evolution. Our brains evolved to survive in a macroscopic world, not to understand atomic-scale phenomena. Expecting quantum behavior to feel natural was therefore unreasonable. This perspective relieved students of unnecessary frustration. Instead of blaming themselves for not understanding, they learned to accept that new kinds of intuition had to be built from scratch. Feynman's role was to guide that construction patiently and honestly. Another powerful tool Feynman used to make the invisible understandable was contrast. He often compared classical and quantum predictions side by side, showing exactly where they diverged. By doing so, he revealed the logic behind quantum rules. They were not arbitrary, they were responses to experimental facts that classical theories could not explain. This comparative approach allowed learners to see quantum mechanics as a necessary evolution of physics rather than a bizarre replacement. The invisible world did not reject logic, it demanded a different logic, one shaped by evidence rather than habit. Feynman also emphasized scale as a key to understanding. He frequently reminded students that many quantum effects disappear at large scales, which is why everyday objects behave classically. This continuity helped bridge the gap between the visible and the invisible. Quantum physics was not a separate universe. It was the foundation of the one we already knew. By showing how classical behavior emerges from quantum rules under certain conditions, Feynman helped demystify the transition between worlds. The invisible was not isolated, it was embedded within the visible. Language itself became a subject of scrutiny in Feynman's teaching. He was acutely aware that words like particle, wave, force, and field carry classical meanings that can mislead when applied to quantum phenomena. Instead of abandoning language altogether, he redefined it carefully. He used familiar terms while constantly reminding listeners of their limitations. This careful handling of language prevented misunderstandings from solidifying into false beliefs. Making the invisible understandable required constant vigilance against linguistic traps. Feynman's approach also highlighted the role of approximation in science. He showed that understanding does not require perfect accuracy at every step. Approximate models, when used consciously, can provide powerful insight. In quantum physics, exact solutions are often impossible, but approximate methods reveal patterns and relationships that deepen understanding. Feynman treated approximation not as a weakness, but as a strength of human reasoning. It allowed the mind to grasp the structure of a problem before drowning in detail. This attitude made the invisible manageable rather than overwhelming. An often overlooked aspect of Feynman's success was his emotional honesty. He openly expressed amazement, confusion, and excitement when discussing quantum phenomena. This emotional transparency validated the learner's experience. Students realized that confusion was not a sign of incompetence, it was part of engaging with reality at its deepest level. By modeling curiosity instead of authority, Feynman transformed the classroom into a shared journey. The invisible world became less intimidating because it was explored together, not imposed from above. Feynman also understood that visualization does not always mean imagery in the traditional sense. Sometimes, understanding comes from imagining processes unfolding in time, or from tracking relationships rather than shapes. He encouraged flexible thinking, where the mind adapts its tools to the problem rather than forcing problems into familiar molds. This flexibility was essential in quantum physics, where rigid images often fail. By expanding the meaning of visualization, Feynman gave learners multiple entry points into understanding. In discussing measurement and observation, Feynman avoided philosophical dramatization. He acknowledged the strange role of measurement in quantum mechanics, but resisted turning it into a mystical act. Instead, he framed measurement as a physical interaction governed by quantum rules like any other. This perspective grounded one of the most puzzling aspects of quantum theory in concrete processes. The invisible did not become magical, it remained physical, even if unfamiliar. Feynman's commitment to making the invisible understandable also influenced how he evaluated explanations. He believed that if an idea could not be explained to a beginner, it was not yet fully understood by the expert. This belief drove him to refine explanations continuously. He tested ideas by explaining them in different ways, to different audiences, watching carefully for confusion. This iterative process mirrored scientific experimentation itself. Teaching became a laboratory for understanding, not a performance. Over time, Feynman's methods reshaped how quantum physics was communicated worldwide. Textbooks, lectures, and research papers began to adopt more intuitive explanations, inspired by his approach. The culture of physics slowly shifted toward greater openness and clarity. While quantum mechanics remained difficult, it no longer felt deliberately inaccessible. The invisible world became a shared challenge rather than a guarded secret. Perhaps the most profound impact of Feynman's work in this area was the change in attitude it produced. Students learned that not seeing something does not mean it cannot be understood. Reality extends beyond sensory experience, and the human mind, guided by evidence and imagination, can reach into that unseen domain. Feynman showed that understanding is not about comfort, but about honesty and effort. The invisible does not yield to passive observation, it yields to active inquiry. In the final sense, making the invisible understandable was an ethical stance for Feynman. He believed that knowledge should not be trapped behind barriers of language, tradition, or fear. The universe belongs to everyone, and its deepest laws should be approachable to anyone willing to think carefully. By refusing to hide quantum physics behind obscurity, Feynman affirmed a democratic vision of knowledge. Understanding became an invitation, not a privilege. Through this lifelong effort, Richard Feynman changed how people relate to the unseen foundations of reality. He did not remove mystery from quantum physics, nor did he pretend that everything could be made simple. Instead, he showed that mystery and understanding are not opposites, they coexist. By building honest bridges between what we see and what we cannot, Feynman allowed countless minds to step into the invisible world with curiosity rather than fear, and with confidence rather than confusion. From the moment Richard Feynman entered formal education, he sensed a tension between genuine understanding and the way knowledge was often presented. Schools, he noticed, frequently rewarded memorization, obedience, and speed rather than depth, curiosity, and honest thinking. Many students learned to repeat definitions, formulas, and procedures without ever asking whether they truly understood what those symbols represented. This troubled Feynman deeply, because for him learning was never about storing information, it was about building a living relationship with ideas. He believed that the purpose of education was not to fill the mind, but to train it to ask better questions. Feynman's approach to learning began with a simple but demanding principle: if you cannot explain something in your own words, you do not understand it. This idea shaped how he studied, how he conducted research, and how he taught others. When he encountered a new concept, he did not try to memorize its formal definition immediately. Instead, he attempted to reconstruct it from first principles. He asked where the idea came from, what problem it was meant to solve, and how it connected to things already known. Only after this process did equations and formal language make sense to him. Learning, in this view, was an active process of reconstruction, not passive absorption. This philosophy stood in sharp contrast to traditional academic culture, especially in advanced science. Many students believed that mastery meant being able to solve problems quickly using established methods, even if they did not fully grasp why those methods worked. Feynman rejected this idea. He saw memorization without understanding as fragile knowledge, easily forgotten and easily misapplied. Real understanding, he argued, was flexible. It allowed a person to approach unfamiliar problems creatively, adapt ideas to new situations, and recognize when existing tools were insufficient. Questioning, not memorizing, was the engine that produced this flexibility. Feynman's own learning habits reflected this belief. When studying physics, he often ignored standard solution techniques at first and tried to invent his own. Sometimes his methods were inefficient or even incorrect, but the process forced him to confront the structure of the problem directly. Through trial and error, he developed a deep intuition that could not be acquired through memorization alone. This habit made him slower in some early academic settings, but it ultimately gave him a profound advantage. He did not merely know physics, he could think in physics. As a teacher, Feynman brought this same attitude into the classroom. He was not interested in producing students who could recite correct answers on exams. He wanted students who could reason, who could identify assumptions, and who could recognize when they did not understand something. He encouraged students to interrupt lectures with questions, even if those questions seemed basic or naive. In fact, he valued such questions highly, because they often revealed hidden gaps in understanding that more advanced questions overlooked. For Feynman, a simple question asked honestly was more valuable than a sophisticated answer repeated mechanically. One of the most striking features of Feynman's teaching was his willingness to dismantle familiar ideas. He did not assume that students' prior knowledge was correct or complete. Instead, he often started from scratch, rebuilding concepts step by step. This approach was demanding, both for him and for his audience, but it was also liberating. Students were no longer expected to accept ideas on authority alone. They were invited to follow the reasoning, to see how conclusions emerged naturally from evidence and logic. Learning became a process of discovery rather than submission. Feynman was especially critical of what he saw as formula thinking, the habit of searching for the right equation to apply without understanding the situation. In quantum physics, this habit was particularly dangerous because equations can produce correct numerical results even when applied without insight. Feynman wanted students to understand what the equations were describing, not just how to use them. He often challenged students by asking them to explain the physical meaning of a result in plain language. If they could not, he considered the learning incomplete. This emphasis on questioning extended beyond technical details to the foundations of knowledge itself. Feynman taught students to question definitions, classifications, and even the goals of scientific inquiry. He pointed out that many scientific terms are human-made labels imposed on a continuous reality. While these labels are useful, they can also create illusions of understanding. For example, naming a phenomenon does not explain it. Feynman constantly reminded learners to look beyond words to mechanisms. This habit protected them from mistaking familiarity for comprehension. Feynman's insistence on questioning also applied to himself. He did not see teaching as a one-way transmission of knowledge from expert to novice. He saw it as an opportunity to test his own understanding. Explaining an idea forced him to confront weaknesses in his reasoning. If he struggled to explain something clearly, he took it as a sign that he needed to think more deeply about it. In this way, teaching became an extension of learning. The classroom was not a stage for performance, but a workshop for thought. Another important aspect of Feynman's philosophy was his rejection of fear-based learning. Many students approach difficult subjects with anxiety, afraid of making mistakes or appearing ignorant. Feynman believed that fear was one of the greatest obstacles to understanding. It discourages questioning and encourages rote behavior. To counter this, he created an atmosphere where mistakes were not only tolerated but expected. He openly discussed errors, both his own and others, as natural steps in the learning process. This honesty reduced the stigma around not knowing and encouraged students to engage more deeply. Feynman also understood that questioning requires time and patience. Memorization can produce quick results, but understanding develops slowly. He resisted educational pressures that emphasized speed over depth. In his lectures, he often spent long periods exploring a single idea from multiple angles. To some, this seemed inefficient. To Feynman, it was essential. He believed that rushing through material created the illusion of progress while leaving understanding shallow. True learning, he argued, often feels slow because the mind is reorganizing itself. His approach to questioning was not limited to scientific content. He encouraged students to question the structure of education itself. Why are certain topics taught in a particular order? Why are certain methods favored? Who decides what counts as important knowledge? By asking these questions, Feynman helped students see education as a human system shaped by historical and cultural factors, not a neutral transmission of truth. This awareness empowered learners to take ownership of their education rather than passively accepting it. Feynman's emphasis on questioning also shaped his views on expertise. He warned against confusing credentials with understanding. A person with advanced degrees could still misunderstand fundamental ideas, while a curious beginner could sometimes see things more clearly. This did not mean rejecting expertise altogether, but it did mean holding it accountable. Experts, in Feynman's view, had a responsibility to explain their ideas clearly and to remain open to questions. Authority should invite scrutiny, not suppress it. This philosophy had profound implications for how quantum physics was taught. Instead of presenting the theory as a finished product, Feynman presented it as an ongoing human effort to describe nature. He discussed historical debates, failed ideas, and unresolved questions alongside successful theories. This contextual approach helped students see science as a dynamic process rather than a static collection of facts. Learning became a participation in that process, not merely a review of its outcomes. Feynman also emphasized that questioning is not about constant doubt for its own sake. It is about seeking coherence and consistency. Questions should be guided by evidence, logic, and curiosity, not by cynicism or contrarianism. He taught students to distinguish between productive questioning, which deepens understanding, and empty skepticism, which leads nowhere. This balance was crucial. It allowed learners to remain open-minded without becoming paralyzed by doubt. In the broader sense, Feynman's rejection of memorization reflected a deeper commitment to intellectual honesty. Memorization can create confidence without understanding, and that confidence can be dangerous. In science, it can lead to uncritical acceptance of flawed ideas. In life, it can lead to rigid thinking and resistance to change. By teaching students to question, Feynman was teaching them how to remain adaptable in a world where knowledge is always incomplete. This approach also made learning more meaningful. When students understood ideas through questioning, they felt a sense of ownership over their knowledge. It was no longer something imposed from outside, it was something they had built themselves. This sense of ownership increased motivation and curiosity. Learning became intrinsically rewarding rather than externally driven. Feynman believed that this internal motivation was far more powerful than grades or praise. Ultimately, learning through questioning rather than memorizing was not just a teaching technique for Feynman, it was a philosophy of life. He believed that the same attitude should be applied to beliefs, traditions, and assumptions of all kinds. By questioning honestly and persistently, individuals could avoid self-deception and engage more fully with reality. In this sense, education was not preparation for life, it was practice for thinking clearly and living truthfully. Through this commitment, Feynman transformed the experience of learning quantum physics. He showed that even the most abstract ideas could be approached with curiosity rather than fear, with questions rather than blind acceptance. By replacing memorization with inquiry, he empowered generations of students to think for themselves, to trust their reasoning, and to see learning not as a burden, but as an ongoing adventure of understanding. Learning through questioning, rather than memorizing, did not end at the classroom door for Richard Feynman. It shaped the way he believed human beings should relate to knowledge throughout their lives. He was deeply concerned that memorization creates an illusion of competence. A person may feel confident because they can recall formulas, definitions, or authoritative statements, yet this confidence often collapses the moment a situation changes slightly. Feynman saw this as one of the greatest dangers in education. When people rely on memorized knowledge, they stop thinking. And when thinking stops, mistakes multiply quietly and confidently. Questioning, by contrast, keeps the mind alert. It forces continuous engagement with reality rather than with stored symbols. Feynman often emphasized that the act of questioning reshapes the brain itself. When a learner asks, "Why?" the mind begins searching for connections, causes, and constraints. This search builds internal structure. Memorization, on the other hand, places information side by side without linking it meaningfully. Feynman understood that quantum physics, more than almost any other subject, exposes the weakness of memorized knowledge. The moment one faces a novel problem, memorized procedures fail. Only those who understand the underlying principles can adapt. This is why he insisted that students wrestle with concepts instead of rushing toward answers. The struggle itself was not wasted time. It was the process by which understanding took shape. Another key element of Feynman's philosophy was his belief that questions must come from genuine confusion, not from performance. He disliked questions asked to impress others or to appear intelligent. Such questions, he believed, often hide real misunderstanding. He encouraged students to ask the questions they were almost embarrassed to ask, the ones that seemed too simple or too basic. In his view, these questions were often the most important because they pointed directly to foundational issues. Quantum physics is full of ideas that sound familiar but behave in unfamiliar ways. Only honest questioning can reveal where intuition silently breaks down. Feynman also recognized that questioning is emotionally demanding. It requires admitting uncertainty, and uncertainty can feel uncomfortable, especially in competitive academic environments. Many students fear that asking questions will expose weakness. Feynman actively worked against this fear by normalizing not knowing. He openly shared moments when he himself had been confused or mistaken. By doing so, he removed the false image of the infallible expert. Learning became a shared human process rather than a test of worth. This emotional safety was essential for deep understanding, especially in a field as counterintuitive as quantum mechanics. In his lectures, Feynman often delayed formal definitions deliberately. He wanted students to first feel the problem, to sense what was puzzling and why it mattered. Definitions introduced too early, he believed, could shut down curiosity. Once a word is attached to an idea, students often assume they understand it, even when they do not. By postponing labels, Feynman kept questions alive. Only after students had struggled with an idea did he introduce formal terminology, which then served to organize understanding rather than replace it. This method also revealed Feynman's belief that misunderstanding is often more instructive than immediate clarity. When a student forms an incorrect mental model and then discovers its failure, the correction leaves a deep impression. Memorized facts rarely produce such moments of insight. Feynman intentionally designed explanations that confronted common misconceptions directly. He allowed students to follow an intuitive path until it reached a contradiction, and only then guided them toward a more accurate framework. This approach required patience and careful pacing, but it resulted in understanding that was robust rather than fragile. Feynman extended this questioning mindset to scientific research itself. He warned that entire fields could drift into confusion if researchers stopped questioning foundational assumptions. Over time, techniques become standardized, methods become routine, and results are accepted without deep scrutiny. Feynman believed this intellectual comfort was dangerous. Progress, he argued, depends on the willingness to ask whether accepted methods still make sense. His own breakthroughs often came from questioning ideas that others had long taken for granted. This habit kept science alive rather than mechanical. He also stressed that questioning should be guided by reality, not by ideology. Questions must ultimately be answered by experiment and observation, not by preference or belief. In quantum physics, where philosophical interpretations abound, Feynman maintained a disciplined focus on what could be tested. This discipline prevented questioning from drifting into speculation detached from evidence. Learning through questioning, in his view, required both openness and restraint. One must be free to ask any question, but also willing to abandon ideas that fail when confronted with facts. Feynman's resistance to memorization also shaped his views on textbooks and formal curricula. He criticized materials that presented physics as a sequence of finished results without showing how those results were discovered. Such presentations, he argued, rob students of the opportunity to think like scientists. Without seeing the questions that motivated theories, students are left with answers that feel arbitrary. Feynman believed that understanding grows when learners see the path of reasoning, including false starts and corrections. This historical and logical context transforms knowledge from static information into a living process. Another important aspect of Feynman's philosophy was his belief that questioning strengthens intellectual independence. A person trained to question does not rely blindly on authority. They can evaluate claims, identify weaknesses, and form their own judgments. This independence was especially important to Feynman in a world increasingly shaped by scientific and technical expertise. He worried that societies could become vulnerable if citizens accepted expert claims without understanding their basis. Teaching people how to question was, therefore, not just an educational goal but a civic responsibility. Feynman also recognized that questioning does not end when formal education ends. Memorized knowledge decays quickly, but the habit of questioning endures. He believed that the true measure of education was not how much a person remembers years later, but how they approach new problems. Do they ask meaningful questions? Do they seek understanding, or do they search for ready-made answers? In this sense, learning through questioning prepares individuals for a lifetime of adaptation in a changing world. This approach transformed how students experienced quantum physics. Instead of feeling overwhelmed by its strangeness, they learned to engage with it actively. Confusion became a signal to investigate rather than a reason to withdraw. Students developed confidence, not because they had memorized correct answers, but because they trusted their ability to think. This confidence was quieter and more durable than the confidence produced by rote success. Ultimately, Richard Feynman's insistence on questioning over memorization was an expression of respect for the subject, for the learner, and for truth itself. He believed that reality is subtle and complex, and that it deserves careful thought rather than mechanical repetition. By teaching people how to question, he gave them tools to approach not only quantum physics, but the world with clarity and honesty. Learning became an act of engagement rather than accumulation, a process of continuous discovery rather than passive storage. Through this philosophy, Feynman ensured that understanding remained alive, flexible, and deeply human. For Richard Feynman, teaching was never a performance designed to impress, nor a ritual of authority meant to reinforce hierarchy. Teaching, in his view, was an act of honesty above all else. He believed that when a teacher stands before students, there is a moral responsibility to tell the truth not only about what is known, but also about what is not known. This principle shaped every lecture he gave and every explanation he offered. He rejected the idea that a teacher must appear flawless or all-knowing. On the contrary, he believed that pretending to understand something perfectly when one does not is a form of dishonesty that damages learning at its core. Feynman understood that science advances precisely because it admits uncertainty. Knowledge grows by identifying gaps, contradictions, and failures, not by hiding them. When teachers conceal uncertainty, students receive a false image of knowledge as something finished and complete. Feynman saw this as deeply harmful, especially in quantum physics, a field built on probabilities, approximations, and unresolved questions. He openly told students when a concept was not fully understood, even by experts. Instead of weakening confidence in science, this honesty strengthened it. Students learned that science is trustworthy not because it claims certainty, but because it is transparent about its limits. This honesty extended to Feynman's explanations themselves. He refused to use vague or decorative language to mask confusion. If an explanation relied on words that sounded impressive but lacked clear meaning, he considered it dishonest. He was especially critical of explanations that replaced understanding with terminology. Naming a phenomenon without explaining its mechanism, he argued, creates the illusion of knowledge. In his teaching, he stripped ideas down to their essentials, even if that process exposed awkward gaps. He preferred an incomplete but honest explanation over a polished but misleading one. Feynman also believed that honesty in teaching requires respect for the learner. Misleading students, even unintentionally, was a violation of that respect. He refused to simplify ideas to the point of distortion. While he made quantum physics accessible, he never pretended it was easy. He trusted that students could handle difficulty if it was presented truthfully. This trust created a powerful bond between teacher and learner. Students felt that they were being treated as thinking adults, not as passive recipients of information. Another crucial element of Feynman's honesty was his willingness to expose his own thinking process. He did not present conclusions without showing how they were reached. He shared his doubts, false starts, and intermediate steps openly. This transparency allowed students to see that understanding is not instantaneous. It develops through struggle, revision, and persistence. By revealing his own cognitive journey, Feynman normalized confusion as part of learning. Students no longer felt isolated in their difficulties. They saw that even a brilliant physicist had wrestled with the same questions. Feynman's honesty also meant acknowledging the emotional side of learning. He did not pretend that quantum physics feels intuitive or comfortable. He openly admitted that many concepts resist classical intuition and may never feel completely natural. Rather than offering false reassurance, he encouraged students to accept this discomfort. Understanding, he taught, does not always feel satisfying in the traditional sense. Sometimes it feels unsettling because it forces us to abandon familiar ways of thinking. Honesty required admitting this emotional reality rather than glossing over it. In the classroom, this approach transformed the relationship between teacher and student. Feynman did not position himself as an authority delivering final truths. He positioned himself as a guide exploring a difficult landscape alongside his audience. This did not diminish his authority, it redefined it. His credibility came not from certainty, but from integrity. Students trusted him because he never exaggerated, never hid confusion, and never claimed more understanding than he possessed. Feynman's insistence on honesty also shaped how he evaluated scientific claims. He taught students that self-deception is the greatest enemy of understanding. It is easy to convince oneself that an explanation is satisfactory when it is not. Honest teaching, therefore, requires constant self-scrutiny. A teacher must ask, do I truly understand this, or am I repeating words? Feynman applied this standard ruthlessly to himself. If he could not explain an idea clearly, he took it as evidence that his own understanding was incomplete. Teaching became a test of truth. This principle extended beyond physics into broader intellectual life. Feynman believed that honesty in teaching prepares students for honesty in thinking. When learners are encouraged to admit confusion, they become more open to correction and growth. When they are taught to hide uncertainty, they become defensive and rigid. Feynman wanted to cultivate thinkers who could change their minds in response to evidence. This flexibility, he believed, was essential not only for science but for responsible citizenship in a complex world. Feynman was also honest about the limits of explanation itself. He acknowledged that some questions lead to deeper questions rather than final answers. For example, asking why the laws of quantum mechanics are the way they are eventually leads to philosophical territory where science has no definitive response. Instead of inventing speculative answers, Feynman drew clear boundaries. He showed students where science ends and where mystery begins. This clarity protected learners from confusing speculation with knowledge. Perhaps most importantly, Feynman believed that honesty makes learning meaningful. When explanations are truthful, students engage with reality rather than with illusions. They develop a realistic sense of what knowledge can and cannot provide. This realism fosters humility without discouragement. Students learn that understanding is always partial, always evolving, and always open to revision. Far from being discouraging, this realization can be deeply liberating. It removes the pressure to achieve perfect certainty and replaces it with the freedom to explore. In the end, teaching as an act of honesty was central to Richard Feynman's impact on science education. He showed that clarity without truth is manipulation, and truth without clarity is neglect. True teaching requires both. By refusing to hide uncertainty, exaggerate understanding, or protect authority at the expense of truth, Feynman transformed teaching into an ethical practice. He demonstrated that the most powerful way to educate is not to pretend to know everything, but to model how a thinking human being honestly confronts the unknown. For Richard Feynman, joy was not an optional decoration added to serious work. It was a central force that powered imagination, creativity, and deep understanding. He believed that science at its best is a form of play, a structured, disciplined play, but play nonetheless. This attitude set him apart from many of his contemporaries, who treated physics as a solemn pursuit burdened by prestige and pressure. Feynman approached it with delight, curiosity, and a sense of fun that never disappeared, even when he was dealing with the most abstract and demanding problems of quantum theory. From an early age, Feynman found pleasure in figuring things out. The act of discovery itself was rewarding, independent of recognition or practical outcome. This intrinsic joy shaped his entire career. He did not choose research topics because they were fashionable or guaranteed success. He chose them because they fascinated him. When he lost interest in a problem, he moved on without regret. This freedom allowed his imagination to roam widely. He trusted that genuine interest would lead to deeper insights than forced effort ever could. Playfulness was one of Feynman's most distinctive traits. He was known for his unconventional behavior, his humor, and his willingness to appear eccentric. Yet this playfulness was not superficial. It was a cognitive strategy. By approaching problems playfully, he kept his mind flexible. Play reduces fear of failure, and fear is one of the greatest obstacles to creativity. When mistakes are treated as part of the game, exploration becomes easier. Feynman allowed himself to try strange ideas, unconventional approaches, and even absurd thought experiments, knowing that most would fail, but some might reveal something new. Imagination played a crucial role in how Feynman thought about quantum physics. The quantum world does not align with everyday experience, and strict logical reasoning alone is often insufficient to grasp it. Feynman used imaginative constructions, mental experiments, visual metaphors, and conceptual stories to explore possibilities. He imagined particles interacting through exchanges, paths interfering with one another, and probabilities adding in surprising ways. These imaginative acts were not fantasies, they were disciplined explorations guided by mathematical and experimental constraints. Imagination, for Feynman, was not opposed to rigor. It was one of its most powerful tools. Music and art were also expressions of this joyful imagination. Feynman played the bongo drums with enthusiasm, not because it advanced his career, but because it brought him pleasure. He drew, painted, and explored creative expression throughout his life. These activities were not escapes from science, they enriched it. They trained his senses, sharpened his perception, and reminded him that understanding is not purely intellectual. Rhythm, pattern, balance, and harmony exist in both art and physics. By engaging with both, Feynman kept his thinking fresh and multidimensional. In teaching, Feynman's joy was unmistakable. His lectures were energetic, animated, and often humorous. He laughed at paradoxes, expressed amazement at unexpected results, and openly shared his excitement. This emotional openness transformed the learning environment. Students felt invited into a living experience rather than subjected to a dry transfer of information. Joy became contagious. When students saw their teacher genuinely enjoying the subject, they were more willing to engage, even with difficult material. Quantum physics became less intimidating because it was presented as an adventure rather than a test. Feynman believed that imagination thrives when it is free from excessive pressure. He criticized academic systems that punish mistakes and reward conformity. Such systems, he argued, discourage creative thinking. Quantum physics, which often requires leaps beyond classical intuition, cannot flourish in an atmosphere of fear. Feynman created mental space for exploration by treating problems lightly at first. He played with ideas before judging them. This preliminary play allowed unexpected connections to emerge. Only later did he apply strict evaluation and mathematical rigor. Joy also protected Feynman from intellectual burnout. Many researchers lose motivation after years of pressure and competition. Feynman avoided this fate by refusing to let science become a source of anxiety. When external demands became overwhelming, he returned to the simple pleasure of figuring things out for their own sake. This inner motivation sustained him through long periods of difficulty and uncertainty. Joy, in this sense, was not a distraction from productivity, it was its foundation. Feynman also saw joy as a form of honesty. Pretending that science is always serious and grim misrepresents the human experience of discovery. Real understanding often comes with surprise, delight, and even laughter. By allowing these emotions into his work, Feynman presented a more truthful picture of how knowledge grows. This honesty made science more approachable and more human. Imagination guided by joy also shaped Feynman's ethical outlook. He believed that curiosity-driven exploration should remain connected to human values. When science becomes purely mechanical or goal-driven, it risks losing sight of its purpose. Joy reminds us why we explore in the first place, not only to control nature, but to understand and appreciate it. This appreciation fosters humility and respect rather than domination. Feynman often spoke about the beauty of nature as revealed through physics. Understanding for him did not destroy beauty, it deepened it. Knowing how a flower grows or how a particle behaves does not make the world less magical. It reveals layers of complexity and elegance that would otherwise remain hidden. This perspective challenged the idea that analysis kills wonder. For Feynman, imagination and analysis worked together to expand wonder. In the end, joy, playfulness, and imagination were not side notes in Richard Feynman's life. They were central pillars of his approach to science and teaching. They allowed him to explore the quantum world without fear, to communicate its mysteries with enthusiasm, and to inspire others to see learning as a source of pleasure rather than obligation. Through this attitude, he showed that the human mind does its best work not under pressure and rigidity, but when it is free to play, imagine, and delight in the process of discovery. Richard Feynman had a deep and instinctive resistance to authority when authority was not supported by understanding. This resistance did not come from arrogance or rebellion for its own sake, but from a fundamental commitment to truth. From an early age, he learned that ideas must stand on their own merits, not on the reputation of the person presenting them. In science, where progress depends on questioning assumptions, this attitude became one of his most powerful strengths. Feynman believed that respect for authority without critical examination was dangerous, especially in a field as complex and evolving as quantum physics. He often pointed out that history is filled with examples of widely accepted ideas that later turned out to be wrong. If scientists had blindly followed authority, many breakthroughs would never have occurred. Quantum physics itself emerged because classical physics, once considered complete, failed to explain experimental results. Feynman used this historical perspective to encourage skepticism, not cynicism, but healthy doubt grounded in evidence. He taught that no idea, no matter how respected its source, should be exempt from questioning. This mindset shaped how Feynman approached learning and research. When studying a theory, he did not ask who proposed it or how famous they were. He asked whether it made sense, whether it matched experimental data, and whether its assumptions were clear. If something seemed unclear, he did not assume the fault lay with him. He assumed the explanation needed improvement. This attitude freed him from intellectual intimidation. Many students hesitate to question established ideas because they fear appearing ignorant. Feynman rejected this fear. He believed that confusion is often a signal that something important has been overlooked. Feynman's willingness to challenge authority sometimes placed him at odds with academic culture. Universities and research institutions often rely on hierarchy, tradition, and credential-based respect. While Feynman recognized the value of expertise, he refused to equate credentials with truth. A Nobel Prize, in his view, did not guarantee correctness. It only recognized past achievement. Truth remained independent of status. This perspective allowed him to remain intellectually agile even as he gained recognition himself. One of the clearest examples of Feynman's challenge to authority came later in his life, during the investigation of the Space Shuttle Challenger disaster. While many experts relied on reports and established procedures, Feynman asked simple, direct questions. He performed a basic demonstration that revealed the failure of the O-rings at low temperatures. This act was not an attack on authority, but a defense of evidence. Feynman showed that truth does not require complex bureaucracy to reveal itself. It requires honesty, curiosity, and the courage to question official narratives. In teaching, Feynman encouraged students to challenge him as well. He did not expect obedience, he expected engagement. If a student disagreed or asked for clarification, he welcomed it. This created a classroom culture where ideas were tested rather than accepted passively. Feynman believed that students trained to question authority become better thinkers. They learn to evaluate arguments, recognize weak reasoning, and defend their own conclusions logically. This skill extended beyond physics into all areas of life. Feynman was careful, however, to distinguish between challenging authority and rejecting expertise. He did not advocate ignoring knowledge or dismissing experience. Expertise mattered, but only insofar as it was supported by clear reasoning and evidence. He warned against the false confidence of those who reject authority without understanding. True skepticism, in his view, requires effort. One must learn enough to ask meaningful questions. Challenging authority is not easy, it demands intellectual discipline and humility. This balance was central to Feynman's philosophy. He believed that science progresses through a constant tension between respect for accumulated knowledge and willingness to revise it. Too much respect leads to stagnation. Too much rebellion leads to chaos. The goal is thoughtful questioning. Feynman modeled this balance by deeply engaging with existing theories while remaining ready to abandon them if evidence demanded it. Feynman also recognized the psychological comfort authority provides. Accepting an established view can feel safe. Questioning it can feel risky and isolating. He acknowledged this emotional dimension and encouraged students to develop courage alongside knowledge. Intellectual independence often requires standing alone, at least temporarily. Feynman himself experienced this isolation at times, but he accepted it as the price of honesty. This attitude had a profound impact on how quantum physics was taught and understood. Instead of presenting the theory as untouchable, Feynman presented it as a powerful but imperfect human creation. He discussed its successes and its unresolved problems openly. Students learned that even the most successful theories are provisional. This understanding prevented blind worship of equations and encouraged creative exploration. Beyond science, Feynman saw challenging authority as essential for a healthy society. When people accept claims without question, whether in politics, religion, or science, they become vulnerable to manipulation. Teaching people how to question responsibly is therefore a moral responsibility. Feynman believed that education should empower individuals to think for themselves, not train them to obey. In the end, Feynman's willingness to challenge authority was not about rejecting tradition, but about protecting truth. He trusted nature more than reputation, evidence more than hierarchy, and understanding more than comfort. By modeling this attitude, he showed that progress depends not on how confidently ideas are presented, but on how honestly they are tested. Through this example, he inspired generations to approach knowledge with courage, humility, and an unwavering commitment to reality. Richard Feynman's legacy is not confined to the equations he derived or the prizes he won. It lives in the way science is taught, learned, and experienced around the world. Long after his passing in 1988, his influence continues to shape classrooms, textbooks, lectures, and the attitudes of both teachers and students. What makes this legacy so enduring is that it is not dependent on a single discovery, but on a transformation in how knowledge itself is communicated. Feynman changed the culture of science education by showing that depth and accessibility are not opposites, but partners. One of the most lasting elements of his legacy is the expectation of clarity. Before Feynman, it was often assumed that difficulty and obscurity were signs of sophistication. Complex ideas were allowed to remain poorly explained, and students were expected to accept confusion as a personal failing. Feynman challenged this assumption directly. He demonstrated that even the most abstract concepts could be explained with honesty and insight. As a result, generations of educators began to see clarity not as oversimplification, but as a mark of true understanding. This shift raised the standard of teaching across disciplines, not just in physics. Feynman's lectures, especially those later published, became a model for how difficult subjects could be presented without condescension. They showed that students could be trusted with complexity if it was introduced thoughtfully. His influence can be seen in modern science communication, where storytelling, analogy, and conceptual explanation are now widely valued. Popular science books, educational videos, and public lectures often reflect Feynman's approach, even when his name is not mentioned. The idea that science should be shared, not hidden, owes much to his example. Another major part of his legacy lies in how he reframed the role of the teacher. Feynman showed that authority in education does not come from dominance or distance, but from integrity and engagement. Teachers influenced by his example are more willing to admit uncertainty, to explore ideas alongside students, and to emphasize thinking over memorization. This has helped create learning environments that are more collaborative and less hierarchical. Students are encouraged to ask questions, challenge explanations, and take ownership of their understanding. In this way, Feynman's legacy continues to empower learners long after his voice has fallen silent. His impact also extends deeply into the practice of physics itself. Tools he developed, particularly visual and conceptual methods, remain central to how physicists think and work. More importantly, his emphasis on physical intuition alongside mathematical rigor has shaped how new generations approach research. Young scientists are encouraged not only to compute results, but to ask what those results mean. This mindset has helped prevent the field from becoming purely technical and disconnected from reality. Feynman's legacy is also evident in the ethical standards he championed. His insistence on intellectual honesty, transparency, and skepticism has become a reference point in discussions about scientific responsibility. He reminded the world that science is a human activity, vulnerable to bias, error, and self-deception. By emphasizing the importance of doubt and verification, he helped strengthen public trust in science, not by promising certainty, but by demonstrating integrity. This ethical legacy is especially important in a world increasingly shaped by scientific and technological decisions. Beyond formal education and research, Feynman's influence reaches into popular culture and the broader imagination. He helped humanize the image of the scientist. Instead of presenting scientists as distant geniuses, he showed that they are curious, playful, flawed individuals driven by wonder. This humanization has inspired countless people who might otherwise have felt excluded from science. Many students who believed physics was not for them discovered, through Feynman's words, that curiosity matters more than background or status. His legacy also lives in the questions he left open. Feynman was careful not to present science as a finished story. He openly acknowledged unresolved problems and fundamental mysteries. By doing so, he invited future generations to continue the exploration. This openness prevents stagnation. It reminds learners that science is not about memorizing what is known, but about participating in an ongoing search for understanding. Feynman's legacy, therefore, is forward-looking. It does not close doors, it opens them. In a deeper sense, Feynman changed how people relate to knowledge itself. He taught that understanding is not something granted by authority or achieved through repetition, but something built through effort, curiosity, and honesty. This lesson extends far beyond quantum physics. It applies to any field where complex ideas must be understood rather than merely accepted. His influence can be felt wherever teachers value reasoning over recall and where learners are encouraged to think independently. Perhaps the most powerful aspect of Feynman's legacy is its accessibility. One does not need to be a physicist to benefit from his ideas. Anyone who has struggled to understand something complex can find guidance in his approach. He showed that confusion is not a personal failure, but a natural part of learning. This message has helped countless individuals persist through difficulty rather than abandon their curiosity. As time passes, specific scientific theories may evolve, and new discoveries may reshape our understanding of the universe. But the principles Feynman embodied, clarity, curiosity, honesty, joy, and courage, remain timeless. His legacy is not tied to a particular era of physics, it is woven into the very act of learning and teaching. Through this enduring influence, Richard Feynman continues to teach long after his lifetime, reminding us that the true power of knowledge lies not in how much we know, but in how openly and honestly we seek to understand.